Yeah, welcome to today's webinar with the title How to Investigate the Thermal Behavior of Biomass. My name is Gabriele Kaiser and I'm working for NETZSCH Analyzing and Testing now already for 25 years, and currently I'm holding the position of the Head of Scientific and Technical Communication Department. The webinar today consists of two parts. The first part is the lecture and the second part is questions and answers. And if you would like to communicate with me and to ask questions, it's possible. And for doing this, please use the question window. Some of you have seen it already on the right side of your screen. You can write down here questions, comments, and also answers, and I can read it and then I will answer it later on. Thank you very much. And before we start the webinar and we go really into detail, I have also a question to you, and the question is, are you using thermal analysis already for your daily work? So please give me just an answer, yes or no, and it would be great if you could add the thermal analytical technique you are using already. Thank you very much for it. Our topic today is biomass, and the definition you can see over here. Biomass is a biological material derived from living or recent living organisms. We have different sources of biomass. The most important source still today is wood, but we also have energy plants, for example. We have residues from agriculture or forestry. We have algae sometimes, or we have organic waste materials. The application area of biomass is also manifold, and you can see it over here. Heating is still the dominating application for biomass, but we also have generating electricity. We have biofuels, here represented by bioethanol or biodiesel, and for example we have also methane gas. The share of the biomass in the total energy consumption is in 2014, it was about 14%. And as I've told you already, this was dominated by heating buildings and also heating industries, and just less than 1.5% was used in other areas such as transportation or energy generation. Analytical methods which are suitable for investigating biomass you can see here on this slide. Let us start with TGA, thermogravimetry or thermogravimetric analysis. This is a method with which we can measure the mass changes of materials as a function of time or temperature. The corresponding instrument is called thermobalance. If we combine thermogravimetry with a second thermoanalytical technique, for example, differential scanning calorimetry, then we come to STA, which means simultaneous thermal analysis, and such an instrument you can see here on the slide on the right side. With STA instruments, it's possible to measure two signals or minimum two signals at the same time on the same sample. So that means, for example, DC and TGA together. With DSC, with differential scanning calorimetry, it's possible to measure phase transformations, for example, so to get information about melting or crystallization behavior of materials. And if we would learn more about decomposition or evaporation processes and to find out what really happens, we can go over to evolved gas analysis, EGA. And this is the third method, what is displayed here on this slide. And we have here different possibilities for adding gas analyzing systems to a TGA or to an STA instrument. For example, to couple an FTIR spectrometer, either in the classical way, so that means via such a heated capillary here, via heated transfer line, or in the Perseus version, what you see over here. So this means this is a direct coupling of an FTIR spectrometer to the furnace outlet of the thermal analysis instrument. As a second possibility, we can also have a coupling with a mass spectrometer. And as a third possibility, what you see over here, this is coupling with a GC-MS system. So that means gas chromatography plus mass spectrometry. And gas chromatography or chromatography in general is a possibility to separate the gas components. And for example, if we enter a GC column with a certain gas mixture, then by passing through this column, we will get a separation and the fragments will leave the column, one fragment by another one with a certain time distance in between. Sorry. The agenda for today's webinar you can see over here. I will concentrate on 4 examples. The first one will be rapeseed straw, and we will have a look on it with TGA FTIR under oxidizing conditions. The second example will be palm kernel shells, and we will have a look on them also with FTIR coupling, but this time with STA FTIR coupling, and we will have pyrolysis and combustion together. Rush grass will be investigated by using TGA GCMS, and the last example will be a thermokinetic study of biomass pyrolysis. Let's start with the rapeseed straw. What we see over here is the TG curve and the DTG curve. The TG curve as blue solid line. We see here several steps, in total 4. One step here up to 200 degrees C with a mass loss of about 9%. A second step up to about 350 degrees C with 57%. A third step up to 550 degrees C with about 29%, and a very small one up to 1000 degrees C with only 1.6% mass loss. The residual mass here is about 2.6% at the end of the measurement. Additionally, we see the so-called DTG curve, and DTG is the first derivation of the TG curve versus time. And the first 3 steps are also represented in the DTG curves as peaks at 75 degrees C, at 332, and at 460 degrees C. The peak temperatures of the DTG curve are often used for temperature characterization of the TG effects. The measurement itself was carried out under oxidizing conditions, but in this time it was not pure air. The oxygen concentration was a little bit less than in air, so that means it was a little bit less than 20%. If you are looking on the curve now, then we can derive from experience, for example, that in the beginning this perhaps can be or could be moisture loss or water loss. Then we have oxidizing conditions, so perhaps this is combustion of the organic matter. But from the TG curve alone, it's not possible really to say what happens. And so we need some additional possibilities, some further measures to find out what is behind these TG steps. And one possibility for further evaluation is to include the so-called CDTA signal. And this is what you see over here. CDTA means calculated DTA signal, and it's really a calculated one. It's derived from the sample temperature, and the sample temperature is compared to the program temperature, and the difference is displayed over here. Calculation of the CDTA signal, the precondition for it is that we have a close contact between the sample thermocouple and the crucible where the sample is put inside. And what we see is that we have here two exothermic effects in a temperature range between 250 degrees C and 500 degrees C, and this indicates that we have really a combustion reaction here. Another possibility to get more information about the reaction, what is going on, is to couple it to a gas analyzing system. And here we have coupling to an FTIR system. And what you see on the slide is a three-dimensional presentation of all measured spectra what we have got. In case of FTIR, we are cooperating with Bruker Optics, and therefore the two software versions, Opus from the Bruker side and Proteus from the NETZSCH side, are communicating with each other, and they are exchanging data. And this is the reason why you can find here in this three-dimensional presentation also a temperature axis, and this is the temperature which is coming from the thermoanalytical system. Additionally, we have also here the TGA curve included. What we are doing now for further evaluation is we cut out from this three-dimensional cube two-dimensional spectra at interesting temperature values. And so, for example, in this case, we cut out a two-dimensional spectrum over here, and over here. So that means where the main peaks are. And afterwards we compare, or we try to compare, these experimental spectra with library spectra for identification. The spectra what we have extracted below 100 degrees C, in particular at 81 degrees C, we can see here in the upper part of the slide in red, and in the lower part of the slide we see the corresponding library spectra, and just by visual comparison we see that it's really very, very similar. It's more or less the same pattern. It's water. So this tells us that below 100 degrees C we really have a release of moisture, we have water loss. If we go to the spectrum what we have extracted at 462 degrees C, then we see that the libraries comparison gives us carbon dioxide, this is the middle one here, and carbon monoxide, this is the double peak, the double band over here. And if we go to the spectrum between 200 and 400 degrees C, sorry, this is the wrong degrees C value, this is 400 degrees C, or this should be 400 degrees C. So the experimental spectrum at 337 degrees C Then we see again carbon dioxide and carbon monoxide, what we have already seen before, but there is something additionally here inside. We have something here in a range between, let's say, 2,600 and 3,000 reciprocal centimeter, and we have something additional over here between 1,000 and 1,800 reciprocal centimeter. What could this be? This would need further evaluation and further studying, but perhaps we have here some CH groups inside. This is for the right side of, sorry, for the left side. Here, for example, this is a typical range for a typical region for carbonyl or carboxyl groups. But in general, we can say it's not only carbon dioxide and carbon monoxide, there's also something additionally inside. Let's go over to the next example, and we have here palm kernel shells, and this is a residue from the palm oil industry. And we have here the powdered material measured with an STA instrument. An STA instrument means that we don't need to calculate the DTA or the DC signal, we really measure it. And you can see it here in blue. This is the corresponding DC signal. We have at first an endothermic effect, and then we have some exothermic effects in a temperature range between, let's say, 250 and 600 degrees C, and then also a small endothermic effect additionally. The measurement here was done at first in argon atmosphere, and at 800 degrees C the atmosphere was switched over to air. So that means above 800 degrees C we have oxidizing conditions and therefore a combustion of the residues what we have over here. The end temperature of the measurement was 1300 degrees C. What we see additionally in this graphic is the TG curve in green, the DTG curve in black, and the so-called Gram-Schmidt plot in violet, and the Gram-Schmidt plot comes from the FTIR experience. From the FTIR experiment. If we are looking a little bit closer to the TG curve, then we see that the profile of the TGA curve is quite similar to what we have seen before, but of course the mass loss steps are different. And this is the reason that we have here up to 800 degrees C pyrolysis, so that means inert gas conditions, and after that we have switching over to oxidizing conditions, and we have a combustion, a burning off of the carbon, of the formed pyrolytic carbon. For getting more information about what is going on during this decomposition steps, we have done also here a coupling experiment, an FTIR experiment. The three-dimensional presentation of all measured spectra, I think you are already familiar with it now. It looks a little bit, of course, it looks a little bit different to what we have seen before. And also here, we will do for further evaluation, we will cut out 3 two-dimensional spectra. One over here, one over here, and the third one in the region where we have oxidizing conditions. The first spectrum, extracted at 287 degrees C, can be seen here in red in the upper part of the slide. We see a carbon dioxide and carbon monoxide. This is very similar to what we have seen before, but here we have also something additional, and we can find acetic acid, for example, as an additional component. For the two-dimensional spectrum, what we have extracted at 366 degrees C, we get this pattern. The experimental spectrum again in red in the upper part of the slide, and here in the lower part of the slide we have several components which give similar spectra. So for example, oleic acid, palmitic acid, this is another name for hexadecanoic acid, or also stearic acid, vinyl ester, they have quite similar patterns and which also fit quite well to the experimental spectrum. So here it's really hard to decide what we really have, or perhaps we have a mixture of all of these substances. In the oxidizing region at 1090 degrees C, we can find only carbon dioxide anymore. Let's go over to the third example, to rush grass. And this rush grass was measured by using TGA GCMS. And for this combination we have several modes what can be used. The first mode is the TGMS mode. So this means we just have a coupling, a connection between the TG or TGA instrument, the TGA thermobalance, and the mass spectrometer itself. And we don't use the GC column. The second mode is the so-called continuous or quasi-continuous mode. And this mode means we are using the GC column for separation, and we inject the gas mixture into the GC within a certain defined time interval. So let's say every minute or something like that. The GC oven is during such an experiment always at the same temperature. The third mode is the so-called event-controlled mode. And event-controlled mode means that we don't have a quasi-continuous injection of the gas into the gas chromatograph. The injection will only take place if something happens, and this is if a certain threshold of the mass loss is exceeded. Then the gas mixture will be injected into the gas chromatography column. The gas chromatography oven will start a heating segment, and during this operation the temperature inside of the thermobalance or of the STA instrument will remain constant. And this is what you see over here in this red temperature profile. And the fourth mode what can be applied is the so-called cryotrap mode. So that means there can also be added cryotrap for concentrating small concentrations. So for concentrating, if, let's say in other words, if you have some components inside with a very small concentration, and you would to increase the sensitivity or to identify these materials, these fragments, you can freeze them at first in the cryotrap, and then afterwards in a desorption step you can measure them. And what we have used here for investigating the rush grass is the so-called event-controlled mode. You see again the TGA curve in green as a dashed line, the DTG curve in blue as a dashed dotted line, and the temperature curve in red as a dotted line. And you can see here also the threshold values, what were used for injection into the gas chromatograph, and the threshold was about 4% per minute. So that means each time the mass loss, or in other words the DTG curve, reaches 4% or has reached 4%, then the gas mixture was injected into the gas chromatograph and analyzed. And during this process, the temperature inside of the thermobalance was stable. And by using this measurement mode, it was possible, for example, at 263 degrees C to get this total ion current chromatogram. And here you see also the temperature program of the GC oven, 70 degrees C isothermal, and then heating to 310 degrees C with a heating rate of 25 Kelvin per minute. And by analyzing this total ion current chromatogram, we got the following hit list. So that means hit quality, high hit quality means high probability that the corresponding fragment, that the corresponding substance is inside. And the highest hit quality here at the temperature of 263 degrees C was chloromethane and dimethylpyrazole. If we did this for the second step, so that means at 312 degrees C, with the same temperature program for the GC oven, then we got this hit quality, so this hit list, for example, and we had again chloromethane, but this time we had also phenol with a quite high hit quality, and again dimethylpyrazole. Let's go over to the fourth example, and this is a thermokinetic evaluation of biomass pyrolysis. Thermokinetic evaluation means we try to find a mathematical model to describe what is going on, and if we have found a mathematical model of description, then we can predict or simulate the mass losses during freely selectable temperature programs. This is one of the TG curves. So we see the TG curve in green as a solid line and the DTG curve as a dashed line, and we see here that we have quite a lot mass loss steps inside. The residual mass at about 900 degrees C, this measurement was completely carried out in nitrogen atmosphere, was about 24%. And if we are concentrating here on this temperature range, so that means between 150 and 550 degrees C, because we can derive from the experiment what we have based on the other experiments, that perhaps this is water loss here. And if we do the same measurement with different heating rates, then we get a picture like this. We have carried out here measurements on the same sample with 5, 10, 20 and 40 Kelvin per minute heating rate. The violet curve is the one with 5 Kelvin per minute, and the red one is the one with 40 Kelvin per minute. And what we see is that we have a shift of the decomposition steps to higher temperatures with higher heating rates. Sorry. And the aim of the thermokinetic evaluation is to find, as I've said already, to find a model to describe the reaction, what is going on. And by using the NETZSCH thermokinetic software, in this case it was possible to find such a model, and the model is displayed over here. We found a 4-step model, one A to B, the second one B to C, the third one C to D, and the fourth one D to E. The first step, a diffusion type, and step 2 to step 4 nth order reactions. You see that this is really a formal kinetics, so each reaction step can be of a different reaction type, and it can be applied to TG curves or to DSC curves, or also to dilatometer curves, or to anything else. But the aim is always to find a good fitting between the original measured data, and these are the colored symbols here, and the calculated curves based on the found model, and the calculated curves are the black ones. And what you can see here is that we have a really good fitting, and the correlation coefficient is given over here. It's 0.999995. And what is possible to do with such a mathematical model? One possibility is, and I have mentioned it already, is to predict the behavior for a freely selectable temperature program. And 2 different temperature programs we will see in this slide and also in the next one. Here we have programmed, or we have simulated heating from 150 degrees C to 300 degrees C, at a heating rate of 150 Kelvin per minute, and then to keep this temperature, to hold this temperature 60 minutes isothermal. So that means very fast heating to 300 degrees C and then to have it isothermal. And we see here the calculated corresponding TGA signal, what we get based on this temperature program. And we see that we have a quite fast mass loss, and finally we end up a mass loss of about 56% after 62 minutes. If we select another type of temperature program, for example, what you see over here, heating from 150 degrees C, to 250 degrees C at a heating rate of 50 Kelvin per minute, to keep 250 degrees C isothermal or constant for 20 minutes, to heat further to 300 degrees C with a heating rate of 5 Kelvin per minute, and to keep 300 degrees C isothermal or constant for 10 minutes. Then we get a mass loss profile, what we see over here. We have several steps, not only one, and after 44-45 minutes we end up with a mass loss of about 66 or 68 degrees C. Oh, sorry, percent. I hope you have seen some interesting information in this webinar. We had a look on 4 different examples. One was the rapeseed straw, the rush grass, the palm kernel shells, and also a thermokinetics evaluation of a biomass pyrolysis. With TGA, it's possible to have a look on the mass changes during the heating. With DEC and also with the calculated DTA signal with CDTA, we can also get information about what happens inside the sample with respect to some caloric changes or some temperature changes, if it's an endothermal or if it's an exothermal reaction, what is going on. And with the gas analysis, with the coupling with FTIR, with GCMS, or sometimes also with mass spectrometry, it's possible to get more information about the gases which were produced or which are produced during the decomposition steps, and also to find out and to get more information what really happens inside the sample. Thank you very much for your attention, and I hope it was helpful and it was interesting for you.